So we're going to look at data types. Now, the first thing we do when we look at data types is we need to kind of mess around with our environment to make sure that we can see everything we need in the workspace. So if you are on the default layout, which you would get to by environment layout default, I want you to, well, I have to do that so you can see what I'm doing. But I want to pull this workspace. This is really, really important. I want to see as much of this as possible, so kind of move things around. Also, right-click on your workspace and make sure that value, size, bytes, and class are all selected and nothing else is selected, because that's really what I'm looking for. So we're going to talk about data types. Data types really, really matter. The gooder at programming that you get. So we're going to take a look. So I've just got some code here, and I'm going to go ahead. I'm going to show it to you, so if you want to write it down, you can. So we'll pretend that happened, and you can pause the video and copy these down, and then I'm going to run it, and then we're going to kind of talk. Okay, so since you did that, run it. All right, and then we're going to talk. Okay. So over here, you see the first thing I did is I just said a equals 1. And it's like, okay, cool, a equals 1. The value is 1. Its size is a 1 by 1, and it's 8 bytes. It's a class of double. Now this is where magic starts to happen. Or not magic starts to happen, but this is where knowledge needs to happen. Okay, so let's say I've got this. So it said that it was stored as a double. Now, a double means double floating precision. And I'm going to give you a very, very teeny-weeny version of this. But basically, some things you're going to need to know is there's 8 bits in 1 byte. So an 8-byte double, which is what we had. So it said that we had 8 bytes in the double. An 8-byte double means that we have 64 bits. Okay, so that literally means that we have 1, 2, 3, 4, 5, 6, 64. Okay, now the way that this is set up, the first one is for the sign of the number, so this is plus or minus. The next 52, well, I guess it depends on the order you do. We'll just say the next 11 are for the exponent, and then the next 11 are for the exponent, and then the next 52 are for the value itself. So to make a very, very long story short, basically this means that we have 64 places to store information to express this number. So the exponent is going to explain like how big the number is, as big as the number can get. And this is largeness and largeness, and this is going to reflect precision. And there's, like, you could just spend like weeks talking about this, and we are not going to. I'm just telling you a teeny weeny bit about it. But basically the idea is in MATLAB, there's a couple things. I have a real max, so that's the biggest number that I can make with double precision in MATLAB, and then I have a real min, that's the smallest number. And if you care about this, Google double precision MATLAB, and you'll get all kinds of articles that'll tell you all kinds of things about it. For all practical purposes, we don't care. But it does come up that if I try to put in 2 times 10 to the 310, it's going to come back as infinity, because my maximum real number that I can do is 1.7 times 10 to the 308. So anything bigger than that is going to come as an error, and that's because basically I have exceeded my largeness. Now, when it comes to precision, since I have, wait, did I say 53 or 52? Can I not add? No, I can do that. 52. Okay. Basically, when we come down to precision, I can get about approximately, say, 53 log base 10, can't spell, base 2, I can get about 16 digits of precision. So if I was going to put that's 18 bits of precision. All right. I want to see that number again. You're going to see 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. You see 16 bits right here, and that's approximately as precise as I can get. The 9 kind of goes away. So I don't even think it rounded off. So you see 6, 7. Oh, the 7 rounded off. Yeah, the 8 and the 9 are gone. So it did round off to the 7 whenever it stored it. But there's information missing. That's really as precise as I want to go. So if I want to say 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, it's there. Okay, let me add a couple more zeros to prove a point. There, now it's gone. Basically, I get to a point where the information is missing, and I can't recover it anymore. And you can do some experiments with it. You're like, okay, and I don't know if I've given you the best example, but if I say y equals y minus 2, then I should get that teeny weeny, oh, not 2. Let's do this. Y equals y minus 2 times 10 to the 18. See, I actually get 0. I don't get that teeny weeny number. So I'm going to kind of show you what I did again. Basically what I did is I took this very, very, very large number times this plus this very, very, very large number. So I got that. Then I subtracted off 2 times 10 to the 18. So I should get these teeny weeny numbers here at the end. And I didn't. I got 0. So basically what's going on here is that I've violated the precision. So there's two things that I can violate. I can violate my largeness by, like we said, having a very, very, what is that? Having a very, very, very big number. Or I can violate my largeness by trying to add some very, very large numbers and then subtracting 2 times 10 to the 18. And then instead of getting that 3, I should get 3, but instead I get 0. Okay, so that's why that matters, and that's why we're talking about data types. Double is about as good as you're going to get. There. So double is about as good as you're going to get in any case. Now, I have the numbers 1 through 10, and 1 through 10, since there's 10 of them, that means I have 8 times 10 bytes. So that's 80 bytes, so that's 80 times 8. So that's 640 bits. I probably could have done that in my head. 640 bits that thing is taking up. C was a 2 by 3 matrix, so it's taking 6 times 8 is 48 bytes, or 48 times 8 bits, so 384 bits. Okay, now that was double precision. Now if I run this again, you see I have 5, and I've specifically said that 5 is going to be a single precision. And what's awesome about this is that it takes up exactly half as many, which makes sense because it's single precision instead of double precision. Okay, which basically means that we've proportionally reduced the bigness and the precision that we can get. So if I was going to I haven't done this in advance, so I don't really know how this is going to go. So we'll play with this and see what we get. I'll put it over here. And then we'll do this again. Whoa, it did all kinds of angry. So you see, I tried to, so basically I've already violated the largeness because it said, no, I can't give you 5, but I can give you 4.999. So let's see if I can pull these down. So I can violate the largeness. There I go. So if I do x plus y minus 2 times, we'll make these 1s. Oops. 2 times 1 times, or 10 to the 9th. 2 times 10 to the 9th. Man, I get all kinds of crazy. So if I get z is equal to x plus y, I get 2, and I don't see those 3's over here, so what happens if I subtract 2 times 10 to the 9th? I should get, well, theoretically I should, but maybe I didn't. 2 times, am I not adding right? 1, 2, 3, 4, 5, 6. I'll just do that, just to make sure I do it right. Those little, there we go. Those little parts should be there, so basically I'm taking, I don't know what that number is, that's 3, that's 3, so it's 100 million. So I'm doing 100 million 3 plus 100 million. and then I'm subtracting off 200 million, and I should get 3, but I don't. I get 0, okay? And that's because I'm using single precision. Okay, I'm going to show you again just to maybe help this make sense, is I'm going to take that off, and instead of doing single precision, I'm just going to do regular precision. And see, it worked fine. Because whenever I use double precision, it is going to have twice as much for largeness and twice as much for precision. Not twice as much necessarily, but proportionally larger. Might even be twice, close to twice. But it can handle it using double precision, but it can't handle it using single precision. So the question is, well, why even bother using single precision? And the answer is because it takes up less space. And if you're doing some huge project where it really matters, and you're running out of memory, out of space, then you are going to want to use the smallest data type that can handle your information, which is kind of cool. All right, so back to this. The next one that we look at is int 8. Int 8, you can see, takes up 1. That means, so it's 1 byte, which means it actually takes up 8 bits. And this is one that we can look at pretty straightforward, which is kind of nice compared to some of the other ones. So if I have 8, so okay, so remember we called it an int 8. Int 8 means it has to be an integer, and it takes up 8 bits. Now this first one is always going to be the sign, so that's plus or minus, which means that we have 7 options here. If you know anything about binary, then you'll know the answer to what I'm going to say. If you don't know anything about binary, just assume that I'm right, because, you know, sometimes that's a good idea. But basically that means that the largest number that I can keep is 2 to the 7 minus 1. If you want to think about why, if I had a 3-bit in binary, that's the number 8 in binary, 7, that's the number 7 in binary, and it's 2 cubed minus 1 is 7. That's the biggest number you can make in binary with 3 bits. The biggest number I can make in binary with 7 bits is 2 to the 7 minus 1, and I don't know what that is, but 2 to the 7, except I can't type, 2 to the 7, I really can't type, minus 1. So the biggest number that I can make is 127. I'll see that if I try to say, all right, let's do an int 8 of 200. It's going to come back as 127 because it's like, wait a second, I'm confused. That's as big as I can make a number. So, so that's just something important to note, is that you've got that limitation there. And that's because the first, and it's not 2 to the 8 minus 1 because the first sign is for a, for your plus or minus. I don't know if we actually have these on here, but there's actually an unsigned int. And that one can go all the way up to, as you might expect, 2 to the 8 minus 1. So I can do an unsigned int of, and so you've actually seen the 255 potentially a lot, but if I try to say unsigned int 400, it's going to say, oh, did you mean 255? Because that's the biggest number that I can make. And again, that's because now for the unsigned int, there is no sign, so I have 2 to the 8 minus 1 options, but I can't make any negative numbers. They all have to be positive. So that's just, you know, you get a little bit, you lose a little bit, and that's okay because it's all for programming. All right, so back to what we were looking at. Let's run this again. This is just kind of fun. So now you've got a complex number. Complex, this is a double complex, and 5 plus 3i is a double complex, which means it takes 8 for the real part, 8 for the imaginary part, so 16 bytes. You can make the complex number an int 8, which means it only takes up 1 byte for the first term and 1 byte for the second term, so 2 bytes total. Let's see, bug. Bug is a 1x3 character string. It's going to take up 6 bytes. This is going to have to do with ASCII. We'll talk about that a little bit. If you want to see what just a regular letter looks like, a regular letter is a 1x1, and it's going to take up 2 bytes. So that's 16, right? 2 times 8 is going to take up 16 bits to represent a B. And its class is character. So I'm going to go back to bug because bug makes me happy. MATLAB is awesome is a 1x17, so it's going to be 2 times 17 is 34. That's how much space it takes up. Here's something you haven't seen before, possibly. This is a symbol, and this is not your standard data type in necessarily in other programming languages, but it's a symbol. It's a 1-by-1 symbol, and we'll probably get into that later. It takes up a lot of space, so it's very, very teeny, and even if I make it only X as a symbol, it's still very, very, very large. Did they even change size? I wasn't paying attention. So it went from 1 to 112. No, it's still 112. So it doesn't apparently matter how big I make it. It's still a 112. All right. Now this is a logical. True, false, true. It's taking up 3 bytes because it's a 1x3 logical. I'm not really sure why the logical takes up so much. If I just say true by itself, I don't think it really, to 1x1, it takes up 1 byte. Seems like it shouldn't quite take up that much space, but it does. I'm not going to care, like in the long term, whether you know exactly how many bytes and bits and everything like that. I just kind of want you to know what's going on. If you ever take other programming languages, they're going to be like, and clearly, int double char, blah, blah, blah. And you'll be like, what? And you're like, what did you learn? You're like, I don't know. Okay, so you've got, so here's something that's kind of cool. So that's the identity matrix. That just has ones down. So if I say I5, that gives me ones down the diagonal. So what's interesting is if I have 1,000 by 1,000 with ones down the diagonal, that actually takes up a lot of space. As you can see, it's 1,000 by 1,000, so it's a 8 million byte double. Now there's something that you can do is you can say sparse, and this is like a whole graduate thesis. Where you talk about how do you store sparse matrices, and basically the idea is if I know that most of these are 0, why bother storing the zeros? Why don't I just store where the non-zeros are? And you can actually do that, and it takes up a whole lot less space. So like if you really get into programming, there's like all this really, really awesome nerd stuff that you can get into, and that's really fun.